In this question, we have a table where a sample has been organized. We have males in one row and females in the second row. Then we have columns that represent the letter grades. And we have a totals row and a totals column. We're asked to choose one student at random and find the probability that the student that is chosen is a male. Oh, I think I wrote this wrong. I think the question was supposed to be a male or a student who got an A. Okay, now because of the word or here, we should know that we should be using the addition rule. That means that we want to calculate the probability of the student being male, then separately count the probability of a student getting an A, and then we want to add the probability, the two probabilities, to get the probability of having a student that is either male or got an A. So the addition rule is adding up the probabilities. So the probability of a male plus the probability of getting an A, and then subtract from that the probability that the student was male and got an A at the same time. So the intersection of the two. That's the addition rule. And remember, it was the word or in the phrasing that told me to use the addition rule. So to find the probability of a male, we want to find all the number of male students and divide by the grand total. So we have in this sample, how many male students? We have 38 total male students. And in the entire sample, we have 76 students. So as a decimal, that's 0.5. So half of the students, you can see that the male and student, the male and female students are equal. So it makes sense that we would have a probability of 0.5 here. And I believe that's just coincidental that they happen to be the same amount. Now the probability of getting a grade of A. So again, we'll want to find all the favorable events. So all the students that had an A, we had 25 students total that had a grade of A. And then in the sample, a total of 76 students. All right, now what we want to do is add the probability of a student being a male, which is the 38 out of 76. And we want to add that to the probability of being getting an A. So that's 25 out of 76. And then we want to subtract the probability that the student who's chosen happens to fit into both categories. And so we can see where there is an overlap in the male students with the A students. So right here is the overlap. 17 students who were males that got a grade of A. So those 17 students were already counted when we counted the male students, the 38 male students, and the 17 were included in the 25 students who got an A. So we have an extra 17 students so far in these two quantities. So we're going to subtract off the 17 out of 76. Now, since we have a common denominator, this works out to be equal to taking all of the numerators and combining them, so 38 plus 25 minus 17, and dividing that by the grand total, which would be your common denominator. So what is 38 plus 25 minus 17? It's 46. So this works out to being equal to 46 divided by 76. Now let's look at another way of doing this. We could have also simply counted favorable events by just using the table. I have to fix this. Let me pause first. As I was saying, count all the favorable events. Now you can see them highlighted here. So if we add up using the sum function, these cells, comma, these cells, notice that I only selected each one of the cells one time, or you could do it one by one like this, comma, this one, comma, this one, comma, this one. And notice that I do get 46. And then there are 46 favorable students that either got an A in the class or were males, and we didn't double count any of those. So then we would be able to figure out the answer by dividing it by the total number in the sample and get that final correct answer. And as a decimal, it would look like this. The round off rule for probabilities in general is 3 significant digits, where you do not count any zeros that lead after the decimal. Any other zeros in between numbers are fine to count as significant digits. So this would round to 0.605 using the rounding rule for probabilities. Of course, your homework questions might give you other guidelines and you would want to follow those. Also, if you were asked to give it as a fraction, you would want to make sure to give a reduced fraction. So these two numbers here can be reduced because the numerator and the denominator of the fraction are both divisible by 2 because they're both even. So that's the first thing I noticed, is that we could cut both of those numbers in half. So we would have 23 over 39, I believe, or no, 38. Half of 70 is 35. Half of 6 is 3, so 38. Okay. So now to check if that is equivalent to the original fraction, I can just do 23 divided by 38 and see that I do get the same answer. As a note, when I am typing into here to show the solution and I don't want it to calculate, all I do is put a little, not a parenthesis, what is that called? An apostrophe first before anything else. That way it'll read everything as text. And then when I want to calculate something, I make sure to just have the equal sign so it'll understand that I'm asking it to do a calculation. All right, so the next question, let's hold. All right, in this one, we have been told that we have a bag full of marbles, and in that bag, 7 marbles are red and 16 marbles are not red, with a total of 23 marbles. And we're asked to select 5 marbles randomly and without replacement. Now, whichever version of the question you get, you could have all these numbers would be different, and you might also be asked to select a different number of marbles. So this problem can be slightly different from example to example, but there are 2 videos already attached to this question in Lumen Ohm. So probably one of those videos should be helpful to you, if not both of them. And then now you have this one. So I will do my best to explain this one maybe a little differently than I did in the previous video that is already attached to the question. Since the student sent me this question, it must mean that the video was lacking in some way. Or maybe it was just that they wanted to see their own numbers done in the problem. So part A is usually not the most challenging part of this. There are actually 3 parts to this question. And I'm going to go through all 3 parts, even though I know that the second part, part B, is probably the one that you will struggle with the most. So first of all, to find the probability of all of the marbles being red, we're being asked to find the probability of red, and then red, red again, and red one more time. 5 marbles that are red. And since we're selecting without replacement and doing multiple trials, that would mean we should use the multiplication rule. Actually, let me rephrase that. The fact that we're doing multiple trials and, we want red and then red and then red and then red and then red after another means that we would want to use the multiplication rule. So what we want to do is find the probability of the first one being red, then multiply that times the probability that the second one is red, understanding that we've already taken one red one out and not replaced it. So red, such that red has already been chosen. So that's conditional probability. This is because we have dependent events. The probability is going to shift for every trial. Then after that, we'll want to calculate the probability of getting a red on the third try when we've already had two reds come before it. Now this notation may look a little intimidating or just a little too busy and kind of maybe throw you off, and it's really not meant to. This notation is supposed to make our lives easier because if we can read what it means and not have to write out all of the words. But essentially what we're doing is, if you can just imagine, you have 1, 2, 3, 4, 5 spaces to place a marble from the bag, and you're going to blindly pick a marble out of the bag. You don't know if it's going to be red or one of the other colors. So you're trying to figure out what's the probability on each one of these selections of getting a red every time. Okay. So we want to get a red on the first try, and when we select the first time, the number of favorable events is 7 red marbles in the bag out of a total of 23 marbles. Now, when we go to calculate the probability of getting the second marble red after we've already taken one red marble out and not put it back, would be 6 red marbles left in the bag and out of only 22 remaining marbles in the bag. And likewise, we're going to keep on reducing both the numerator and the denominator for all of these. And I'm just going to pause while I fill this in. Okay, so I'm almost done here. I have been typing in the fractions so that we can see how we calculated everything. And because I didn't want it to calculate as a decimal, I put a parenthesis in front of each of one of these. If you ever forget to put a parenthesis and you don't use an equal sign, it's going to create date format, and that'll be very confusing for you and annoying because then you have to keep changing the format of the cell back. And so what I mean is, if I were to just do 7 divided by 23 over on the side, it would turn into July 23rd. And then if I go in and go, oh, I forgot my equal sign, and I wanted to calculate 7 divided by 23, so I'm going to use my equal sign now, it's still understanding it as a date. It's really annoying, but you can just use Control Z or the undo button, and it should function fine again. See? And like I said, if you don't want it to actually calculate, just put a parenthesis in front of whatever you're typing and it'll recognize it as text. And if all else fails and you have a date format that you don't want, for instance, you can right click it, choose Format Cells, and then go into the number and just make it general or number, however you want to do it, with as many decimal places as you want. There's plenty of options there, but that would hopefully be a last resort. Usually, if you do that by accident, you can just press undo. So I've already put in all the fractions, and now I went ahead and also calculated them by doing the division using the equal sign first. I'll do this last one here. And so now I have individual probabilities for each of my trials. And with my multiple trials that are done in a row, I want to have all of these things be true at the same time by the end of my 5th try. That means I'm using the multiplication rule, and that just means I need to multiply these numbers together. Now, I can do that by multiplying all the numerators. 7, let me show it this way first. 7 times 6 times 5 times 4 times 3. and then take that as a quantity. I forgot my parenthesis in the front. So as a quantity, I'm going to divide that by the quantity of the product of the denominators. 23 times 22 times 21 times 20 times 19. Okay, now that's all well and good, but a faster way to do it if you're using Excel is to use the product function. So just like we used the sum function to add cells together, we can use the product function to multiply cells. This only works if your numbers are in their own separate cells like we have here. So now I can just select all my cells that I want to multiply together and get this result that is the answer to part A. Okay, and then you can round it to 3 significant digits, and actually the number of decimals that are showing now is 3 significant digits. I made it a little bit bigger so that I could see more. So rounding this to 3 significant digits, you ignore the 3 zeros that came after the decimal place and you start counting at the 6. 6 to 4. So to round it to 6, I meant to say to round it to 3 significant digits, it would be 6 to 4. All right, now that was part A. Now let's look at part B. Part B says to, actually, you know what? I like to do part C before I do part B because part C is so easy compared to part B. And part C is actually just like part A, except it's from a different perspective. So here we are asked to find the probability that none of the marbles are red. Okay, so if none of the marbles are red, another way of saying this is that all of the marbles are not red, right? So with my 1, 2, 3, 4, 5 selections that I'm going to make here, I want them to all be not red. And I'm going to do this the same way I did the other example. I'm going to start with the number of not red marbles, and I'm going to choose 5 without replacement. So I'm going to go from 16 on the first try to 15 not red marbles on the second try, and 14, and then 13, and then 12. Is that 5? Yeah. So now I've chosen 5. Make sure I counted right. 16, 15, 14, 13, 12. And then divide that by the denominator descending from 23 total on the first try, 22 on the second try, 21 on the third try, 20 on the fourth try, and 19 on the fifth try. Okay, so that is how you get the answer, just like part A, really, right? No huge deal on that. So that's it. Okay, now let's move on to part B, which is the hardest part. Part B asks, what is the probability that exactly, let me bold this or caps it, exactly 2 marbles are red. Okay, so this is interesting, right? Because exactly 2 just means that order doesn't matter, but somewhere in your 5 marbles, you have 2 that are red. So then the number of favorable outcomes is a lot bigger. Before, we just had one favorable compound outcome in both part A, just that all of them were red. That's just one compound outcome that's favorable. Same thing when we wanted all of them to not be red, just one way to get that to happen. But now we have multiple favorable outcomes. So how many do we have? Well, let's think about different ways this could happen. So we could do the first 2 red. We could do the last 2 red. We could do the 2 on the outside red. We could do alternating red with not red. Starting with the first one, then we could maybe do it with the second one. And then maybe we could do it with the third one. Does that work? Yeah, so I'm counting and coming up with all these different ways. We could do the two in the middle that are red, like this, and then maybe like this. All right, so I'm just trying to figure it out. How many ways are there? I've already counted 8 ways, and I'm not sure if I've thought of everything. So one way, or the best way to tell, since order doesn't matter, I don't care if the first two are red or the last two are red. I just want two red, exactly two red. So order does not matter, and I am doing it without replacement. So whenever you are selecting without replacement, and they didn't say this, but by understanding the way the problem works, order does not matter. So that means we can use combinations for this part of the problem. So combinations, the combinations formula is programmed right into Excel. And that's just the combine function. And then you're supposed to put in the number that you're going to select, or the number of items, and then the number that you're going to select. So here it works a little differently than in some other problems. What we're going to do is we're going to think of it in this way. We have 5 spaces to fill, and we want to fill 2 of them with red marbles. Okay, so by doing that, we get 10. So if we thought a little harder, we could probably come up with 2 more ways. We thought of 8 so far. We could probably come up, we can definitely, I shouldn't even say probably, we should definitely be able to come up with 2 more ways of getting exactly 2 red marbles. And I don't know if it's worth it to even look, but I know there's 10. Okay, so if there's 10 ways for this to happen, that makes me a little uncomfortable because basically what we're saying is that it would be favorable if the first two are red, or the second or the last two are red, or the two outside ones were red, and so on, right? So I'm using the word or because I want you to get that we are going to have to use addition here. So what we want to do is find the probability of each one of these outcomes and then add them together. Okay, so by this point you're going, okay, wait, I have to calculate 10 different probabilities and then add them together. This is going to take a while. Well, no, actually, because luckily it turns out that if you calculate each one of these probabilities individually using the multiplication rule like we did before, you're going to find out that every single one of these 10 outcomes has the exact same probability of occurring, which is awesome because that means that if I do it once and I calculate 2 reds and then 3 not reds, I can just add it to itself 10 times. In other words, 10 times whatever this is. Okay, so I'm going to find the probability of the first outcome I thought of, which is the first 2 marbles being red. So like I did before, I'm going to think, okay, so I'm going to select a red marble on the first try, and then a red marble on the second try. And since I had 7 when I tried on the first try and left 1 out, I now have 6 red marbles to choose from on the second try. Then I'm going to choose, I've already chosen 2 red ones, so now I'm going to choose, the rest are going to be not red. So I'm going to do 3 that are not red. And on the first choice of my not red marble, there's 16 in there. So I'm going to have 16 and then 15 and then 14. So there's my 3 not red marbles. Then I'm going to divide that by that same denominator that we did before, where we just start at 23 and we keep reducing it down until we have 5 selections. So 23 is on the first try, 22 marbles in the bag on the second try, 21, then 20, then 19, and now we have the probability of getting the first 2 marbles red. And now I know that this probability is the same for all of my other 10 outcomes. So I'm just going to add all those together, or in other words, multiply that times 10. So the answer is 10 times this probability And I'm all done. I hope that was helpful to you. These were the only two questions I had from lesson 5 this week. So I hope you all are having a good experience with your lesson 5, and I will see you in the next recording or during my Zoom office hours. Bye.